Good evening. We will wait for 1 minute. Welcome.
Shall I kick off, Hammond?
Yes, please.
Okay. Thank you very much, Hammond. Thank you for helping us today. Good evening, everyone, and thank you very much for joining us tonight on our Zoom and YouTube channels. I'm Iman Abisab. I'm the chair of the Institution of Structural Engineers for the UAE Regional Group, and I would like to welcome you all. This is our third CPD event for this year, 2025. And this CPD will provide us with insights onto crosswind impact on tall buildings design. The talk will specifically discuss the calculation of crosswind loading, wind tunnel testing, and mitigation measures with some practical examples as well. Our speaker tonight is Dr. Suresh Kumar, who is currently a Principal Vice President at RWDI. Dr. Suresh holds a master's, a PhD, and a postdoctorate in wind engineering. He's a member of the Professional Engineers Ontario. He is also a member of the ASCE, American Society of Civil Engineers. He was an adjunct professor at Concordia University in Canada. And most importantly, he's a leader in the field of wind engineering with over 35 years of international experience as a wind engineering researcher and consultant. He's worked on several iconic structures, many tall buildings worldwide, including the Burj Khalifa, world tallest tower in Dubai. Dr. Suresh has also numerous publications and numerous contributions to conference presentations as well. Before I hand over to our speaker, I would like to thank our two sponsors this year. Hempel, who is a supplier of durability and intermittent fireproof paint. Hempel remains our gold sponsor this year. And our new sponsor this year, Arabian Gulf Steel Industry, AGSI, who is a carbon neutral and net zero steel manufacturing facility based in Abu Dhabi, and AGSI is our silver sponsor this year. Our talk will extend for around about 45 to 50 minutes, and we will take the questions at the end of the presentation. I am now ready to hand over to you, Dr. Suresh, if you'd like to kick off. Thank you.
Thank you, Iman, for the kind introduction. And first of all, thanks to Institution of Structural Engineers UAE chapter to arrange this. And special thanks to Iman, Hemant, and the rest of the team at your side. Plus, Nirupama did a great job as well to connect this way. So I had to thank her as well. So without further ado, I'm starting my presentation. This is essentially one of the important stuff in tall buildings, actually, crosswind loading, which is one of the nightmares of those who are designing such type of buildings. So I thought of sharing my experience because I am in the industry for the last 25 years and worked on a number of tall buildings. So how do you really deal with the crosswind loading? That's what I'm going to be sharing. It's kind of fundamental. Time to time, I may get into a little bit of details, but not too many equations or anything. So as far as tall building is concerned, sky is the limit how far you can go up, because nowadays people are trying with super high rises. Now, before that, I mean, in 9/11, I think everybody might be remembering 9/11 incident. So we thought that is going to be the demise of huge towers. However, what we have seen in the past 25 years after that incident is biggest surge in construction in tall buildings. Nearly half of the world's skyscrapers have been built since 2000. And now we are even thinking about vertical cities. We want to live and die basically in cities like this, live on floor, shop on another floor, and attend parties on another floor, etc. and etc. So the idea looks a bit crazy, but I mean, it can happen. So there are projects like that they're planning, at least in the planning stage at this point. And as you all know, wind is the key lateral load whenever the, buildings are super tall or taller. Basically, you can say roughly more than 30 floors or 40 floors is going to be governed by wind. And previously, we used to talk about only strength all the time, but nowadays, I think serviceability is also a serious issue because sometimes it may pass strength wise, but it may not pass serviceability wise due to deflection being exceeded or even acceleration has some issues as well. So now you can see why we are interested in such tall building, wind loading on tall buildings. You can see when wind is blowing, there is a chance that people can perceive motions. So this is one of those videos taken not on a super tall building. This is, I think, of the order of 170 meter or 180 meter tall building. When the wind is blowing, the chandeliers are moving. So people are not noticing maybe there is some party going on. So nobody is paying much attention to the chandeliers. But this is not the case when you are alone on a bedroom. Something is moving, you can immediately come to know something is moving and you'll be really alarmed. So it's all about the perception and your surrounding scenario. Because if you are on a group, you may you may be tolerant to take more motions, but if you're alone, you're not willing to take more motion. And there's another incident. I mean, I'm showing a video where you can see people come up with swimming pools and jacuzzi without realizing that if you don't have proper parapet, the water can spill over during wind. So it can, in this case, it is one of the worst scenario. It is going over the swimming pool. So essentially, the water is going inside the apartment. So now wind flow on a building. So when you talk about wind flow on a building, so let us talk about some fundamentals. When you look at the code or you think about estimating load on a building, you're going to be looking at basically a long wind load. That is means the wind is pushing the structure in the direction of the wind, in the direction of the wind. That is a long wind. You can also get some loading in the crosswind direction. That is due to vortex shedding. So that is also very significant, and you can also get torsion. So all of these three components will be acting all the time. The proportion at which it acts is a different question because it's not going to be happening 100, all of them peaking at the same time, which is not going to be happening. But it will happen to a certain extent. When 100% long wind is happening, maybe you may not get 100% crosswind, etc. etc. Not going into the area of load combinations or anything like that, but all the three will act all the time. And as you know, in certain code, avoid this. Certain code says, okay, only long wind 100%, only crosswind 100%, and things like that. So, which is not completely correct because all the time you can get all three components. So today we are going to be discussing only crosswind. We are not going to be addressing the rest of the type of loading. So this is the content of the presentation. As you can see, crosswind phenomena. So let us talk a few things about the flow physics behind the crosswind phenomena. We can also talk about how do we estimate or preliminary assessment of crosswind loading, and obviously followed by wind tunnel testing. A little bit more physics of crosswind spectra, crosswind spectra, and finally to mitigation, because you can always get some high loading, but how do you mitigate? What are the various options you have? So that also will go through. Everything is kind of fundamental. I'm not going to get into too much of a detail. So a crosswind phenomena. So let's talk about some physics here. So which we just discussed. So when you have a long wind, so it's going to push the building. So the building is going to be oscillating in the direction of the wind. And this one is well addressed in the codes, okay, regardless of which code, Canadian, any type of code you take, I think these are well addressed. You can reasonably compute these things quite well, I would say, using codes. The only issue is if you have a lot of surroundings, obviously your load is going to get decreased. I'm quite sure that you won't be able to get out of the code. For that, you have to do internal tests. But other than that, I mean, you can get a fairly good idea about long wind load from the codes and standards. And then you go to the crosswind loading. What happens is when wind is coming and vortices are being shed on the edges, and the building is going to oscillate in the crosswind direction of the wind. The wind is coming this way, but the building is moving in the opposite direction, the crosswind direction. So this is the loading we are going to be talking today mostly, and this can be quite high compared to long wind at times. And so far I have seen even more than 3 times compared to long wind in certain cases. So let us delve a little bit deep into it. So here I'm showing some spectra here. Spectra is more like this is a energy content in your signal, basically. Because whenever you measure something in wind, it is going to be some kind of time series. So if you want to know what is inside the time series, you go to frequency domain, plot the spectra, you'll come to know, okay, the energy is concentrated in certain frequencies, or is it spread out for various frequencies? So if you look at the long wind, you can see the spectra is more broad-banded. So you have energy content at different frequencies. Actually, my x-axis is reduced frequency. It is kind of a non-dimensionalized frequency. You have to multiply the frequency with the dimension divided by the velocity. So that's a reduced frequency. You can see it is spread out quite a bit. This is more like a white noise. It's not exactly white noise, but similar to a white noise, I would say. But then when you look at the crosswind spectra, you can see it is having a very high hum at certain frequency. Energy is all concentrated at certain portion. So if let us say your building frequency is also falling into the same portion, that is when the trouble starts. You can get huge oscillations and you can get huge loading out of it as well. But as you know, many cases, especially in tall buildings, these spectra is not too narrow banded. If you look at the bandwidth and all of those things, you can realize that this is not a pure vortex shedding. This is vortex shedding mixed with buffeting. Definitely there will be some buffeting. And so it is all mixed kind of a time series. But still there is a very decent hum that you can see all the time when you have such kind of a phenomena. So that's what you're seeing in this case. So you can see there is a huge hump, and if your frequency falls at exactly the same place, then this is a problem. So this is again, the vortices are being shed around a circular cylinder. So wind is coming, it is oscillating the crosswind direction. It's more like chimney. These are applicable in chimneys. So you can see the motion, the crosswind direction. Okay. And then when you record the time signal, the time series, you'll see it is like regular vortex shedding. This is a peculiar frequency at which these vortices are being shed, and you can easily calculate the rest of it. If it is pure vortex shedding, then your peak is also very easy to find out. But if it is mixed with buffering, then your peak factor could be not exactly 1.4, it could be 3.5 also sometimes. So once again, I mean, this is the phenomena. So the vortices are alternate shedding of vortices on both sides of the body, which is causing the body to excite in the crosswind direction when wind is blowing in this way, which is causing this particular hum. And the intensity of this hum depends a lot on many other factors, okay, which we'll discuss in the later slides. Okay, the influencing parameters. So let us look at what are all the stuff which is going to be influencing that hum. Definitely geometry is one of the stuff. Streamline shapes versus bluff shapes. Because our buildings and I mean, the rest of the today is a tall building, so we're not going to be talking about other types of structures. And tall buildings are more or less bluff bodies. It has sharp corners or some cuts, etc., and etc. You have fins, you have all kinds of shapes. So this is bluff. It's not like a streamlined shape like a aircraft wing, for example. That's a more streamlined shape. So this is one of the issue. So when the geometry is getting roughened and you have some corner modifications or some other stuff which we'll be talking later, then you can have an influence on the crosswind oscillations. Surrounding is another issue. If your surrounding is quite heavy, I mean, especially in places like Dubai and Chicago, New York, etc., you have too many surroundings. The surroundings will be helpful in reducing the crosswind issue because your surrounding will take care of the oncoming flow and it will disturb the vortices. It will create more chaos inside the city, and which will be probably helpful for reducing the crosswind issues. Upwind fetch roughness, that is oncoming turbulence. So rougher the terrain, higher the turbulence. Higher the turbulence maybe will reduce the vortex shedding intensity, which will be helpful. So if let us say your building is sitting right at the edge of seashore, definitely you can have more crosswind compared to that the same building is sitting inside in the middle of a city, because in the middle of a city you can get a lot of turbulence, which will be helpful in reducing the intensity of vortex shedding on a tall building. Structural properties has its own influence, frequency, stiffness, mass, damping, all of these having some influence as well. So it is quite complicated if you think about it, because it's not easy to predict this. Okay, so we'll talk more on that. Complex interactions between all of these parameters. Okay, now a little bit more theory, Stahal number. So people might be thinking, okay, can we predict the vortex shedding frequency? It is possible to predict the vortex shedding frequency so that you can also, let us say you're planning a building, you're coming up with a building with certain dimensions. You can estimate, okay, on what velocities this building will have some problem. You can estimate in advance actually using this particular technique, Stahal number. This equation basically is S is a Stahal number, F into B by U. F is the vortex shedding frequency, B is the width, and U is the wind speed. You can easily calculate at which velocity or which frequency the vortex is going to be shed out of this particular body. That's entirely depending on the speed, width, and the Stahal number. So the Stahal number is 0.1 typically for square and rectangle buildings, and it is about zero point 0.2 for circular shapes, because the shedding is very different for a sharp edge object in comparison to a circular object. So regardless of how many times you do the experiment with various B's and various U's, finally you're going to get similar numbers, so Stahal number for a particular shape. There is a beauty of this equation. This has been all proven long back by the rest of the fluid dynamics researchers. Reduced frequency is nothing but a non-dimensionalized frequency. You have to multiply with the width divided by the velocity. So there is no unit for the reduced frequency. And you can say the reduced velocity is the inverse of the reduced frequency. So you just inverse it, that is the reduced velocity. Why I'm saying all of these things is since you are looking at codes, the codes may be sometimes mentioning about reduced velocity rather than reduced frequency, especially Australian code. 10 is being used for square and rectangles. You can see the hump in the Australian code is always around 10. So that is the 1 divided by 0.1 is 10. So that is the reduced velocity. 5 for circular cylinders, so that is 1 by 0.2. So expect to have some hump in the spectra at these reduced velocities. That's what Australian code is showing. I'm not aware of any other code which is showing such spectra. So RV is calculated based on building frequency. Getting closer to the hump will have higher response. So like I said, I mean, there is a vortex shedding frequency and the building frequency is coming closer to that. You can get very high response. There's another parameter which you need to be aware of too, actually. There are different things. So whatever I said before, the Stahal number, that is more of a aerodynamic kind of a parameter because that depends on the shape actually. But this is not based on the shape. This has nothing to do with the shape actually. This is all to do with the structural properties. So m is the mass, eta is the what is the symbol here? Lambda is not lambda. This is the eta is the damping. So this is called sometimes mass damping parameter. Okay, so if the mass is less, obviously the structure will move in wind. And if the damping is less, also it can move in wind. So that's why this parameter is also very important, Scroton number. So you have to look at both aerodynamically as well as structural wise, whether there is going to be significant motion is there or not. So sensitivity of motion and amplitude depends on SE. SE is the Scroton number. So this one, I think we have to pay some attention to that. If the structure is very lightweight, low damping, we have an issue, especially with the, let's say, steel structure. Steel structure, typically the density is very low, the mass is low, damping is also low. So likely the Scroton number is going to be not in a safe region if we are not careful with. For instance, higher Scroton number leads to reduced VIO response. So uh, this is kind of a rule of thumb. If the AC is above 5, there is a possibility of positive aerodynamic damping. And a force spectrum from rigid model test probably is sufficient for response prediction. So the aerodynamic damping, this is another parameter because we always talk about structural damping. Whatever the damping that I am showing here is a structural damping. But you can also get some aerodynamic damping. If the structure is moving in wind, the air can really push back the structure, so which can give some positive aerodynamic damping. But when the mass is too low and the Scroton number is getting reduced and reduced, there is a chance of getting negative aerodynamic damping. It will basically take away your structural damping and the response can increase significantly. So that is a danger. Fortunately, I think most of our tall buildings are heavy. As you know, I always talk about the mass. When you, any typical tall building that you take, even one floor is minimum 500 tons. And nowadays we are seeing 2,000, 3,000 tons and or one floor. Okay, even 5,000 I have seen recently. One floor is 5,000 tons. So that's significant. So when you calculate Scroton number, then you will see that these are, higher Scroton numbers where the motion chance is less, but still you can get some positive aerodynamic damping because it's going to push the structure back. So there is a chance, depending on the slenderness of the building. And if the building is too slender, that is when I think these things will kick in. But when the AC is between around 2.5 to 5, there's a possibility of negative aerodynamic damping. And see, nothing is written in stone, so we cannot go with exact numbers. But like I told you, I mean, Scroton number is not the only parameter which decides whether there is an aeroelastic test is required or not. You had to also look at aerodynamically because that has its own influence. And Scroton number is more on the structural side of things. So you have the mass damping parameter. But if the AC is very low, below 2.5, instability is expected. You can have some instability. So that means the response will never come down. It takes off actually. And then which will eventually end up the failure of the structure. So we never wanted to go into that region and we wanted to arrest any instability. So we had to kind of estimate the instability and then try to get rid of the instability using various mechanisms, which we'll discuss later. So now we roughly, I mentioned about the physics of the flow. There are a couple of parameters to be mentioned, especially the shape. And the second thing is structural parameters like Scroton number. So let us look at how do we estimate this initially. I think the best thing is to go into a code and try to estimate the crosswind. Um, there are very limited information in the code, but at least Australian code has very good information, I would say. A crosswind base overturning moment, they have a nice equation. It's a very easy equations, I would say, because everything is very clearly written in the code. You can easily estimate the crosswind for spectrum coefficient using the nowadays you can use the equation to compute the CFS. Before they had a graph. The graph is like very difficult because it's a log plot, which is quite difficult sometimes to get the right number out of the graph. But now they have an equation. It's very simple. You can just plug in the numbers. You can get the CFS. You can calculate it. And you can also calculate the static crosswind force using this particular equation. I'm not going through the equation in detail, but it's very simple. I mean, all the parameters are well written in the code. Lastly, a crosswind acceleration. This particular equation is not there in the 2021 code. But I derived this equation based on little information out of these two. One could derive this. And previously, I think in 1989 code, if you look at the Australian code, they have an equation for acceleration, but not exactly the same equation, but very similar equation, I guess. But you can easily derive because you know this is mostly inertia. So you can say mass into acceleration is your inertia. And so likewise, you can compute backwards the crosswind acceleration equation. And square and rectangle buildings with aspect ratios between 3:1:1 and 6:2:1. This is what they have been covering. They don't have any coverage for the rest of the aspect ratios. And also everything in isolated condition, buildings less than 200 meter. Okay, that is also because nowadays I think most of the buildings are above 200 meters. So the problem is buildings taller than 200 meters with unusual shapes. No building is nowadays square and rectangle and with surroundings. So what do you do? Okay, that is very difficult to answer, but at least I would say you can utilize these equations as a preliminary estimate. That's what I would do. And there's an example which I think taken from one of my papers. I'm plugging in certain numbers like height, width, and terrain, and etc. To calculate crosswind load on this particular tower. Here, the aspect ratio is 6, 150 divided by 25. And then you can step in line by line. You can use it like basic wind speed, terrain multiplying factor, the rest of the parameters like peak factor, turbulent density, etc., etc. And then you can easily come up with your MC, which is the base moment, crosswind moment. I cannot say this is a huge number depending on the case. And then you can also calculate the crosswind acceleration. I have calculated the crosswind acceleration. In this particular case, it is 33 millig. So if it is a residential tower, this is completely out of the comfort line because you want it to be within 18 millig. So you are already 33 millig. So this is not very good. But the issue here is again, I said the width, but I never said anything about the shape here because I'm assuming this is a square shape. Okay, if it is not square, then the trouble starts because you don't know whether you exactly hit this number when you do a wind tunnel test. Because if the shape is different, then obviously your number can be different. So the other technique one can use at the preliminary stage is CFD. So we do have our own CFD package orbital stack, which can be utilized to calculate the crosswind. So here there are lots of advantage because you can have all the surroundings and you can have the proper shape and you can simulate it for various directions and calculate the crosswind, whether there is any crosswind chance is there or not. You can find out that. So which is quite good because it is taking care of the actual geometry, including the surroundings. So you're basically avoiding a lot of uncertainties in terms of the shape or the surroundings. So I would say this is one of the best tool to utilize at the preliminary stage, not in the final stage. And there are models one can use. I think when you are talking about this crosswind, definitely you have to use LES method for your simulations. So you can see certain simulations that we have done at our lab in estimating crosswind oscillations of structures. Now, this is the ultimate one. So you have the preliminary assessments already done. Now you can move into internal testing. So in internal testing, typically we start with the rigid model test. So you can do rigid model tests. When you talk about overall loading on a building, the loading is two types. One is the mean loading and the fluctuating loading. So the mean loading is mean loading. It's more like a deterministic static loading. Fluctuating loading is a fluctuating load, as the name states. And you can see there are two types of fluctuations, background fluctuations and resonant fluctuations. In rigid model test, background fluctuation is also, we can get it out of the tunnel, but resonant fluctuation, you need to compute it. It's not anything new. We have been doing this for years and decades. Actually, the theory is all well written. We can utilize either HFPI or force balance method. Both of them, you can use it. Or in some cases, you have to also, you can get from the resonant loading from the wind tunnel by using aeroelastic modeling. So in Burj Khalifa, we have done first the rigid model, then later on aeroelastic model. This is the aeroelastic model that you are seeing with the crane in place. The crane is also aeroelastic. It has its own spine, and we wanted to find out the tie load, which is the interaction between the crane and the barge. So we had to get the tie load, which is happening in this crane. And this is one of the case study I'm showing, HFPI study. This is the height of the building is 140 meters. The aspect ratio is 7, and scruton number is 8.5. Scruton number 8.5 is not small, actually. It's relatively high. But still, we are getting a nice hump at this location, which is 170 degree. There is a crosswind happening in MOI, actually. So the vortices are being shed on the side of this building, and it is oscillating the building in the crosswind direction. So by looking at this, immediately you know this is a crosswind because you have zero mean, because it is a symmetric flow. So it is causing a hump. So that is a crosswind location. You have another crosswind here at around 350, 340 degree, but it is not as huge as the 170 degree. Maybe because your upstream terrain could be different, because here it may be suburban, here it may be open water. So that can have an impact in terms of the hump. You can easily see this from the spectra. As I told you, I mean, the spectra has two narrow banded, so that means the vortex shedding is very severe. So if it is kind of broad banded, so it is a lot of buffeting is mixed with the vortex shedding, so you have a little bit broadband spectra. So this spectra is not too peaked spectra, but still it is fairly peaked. In this particular job, the acceleration was high, actually, beyond the limits. And if you want to look at where this is all happening, so you can also plot the moment. This is the moment MOI versus the wind speed at 600 meters. So you can see there is a hump, kind of a response. So this is very typical for vortex shedding induced oscillations, because otherwise typically it will go like this only. It is more like flat, or you can say it's kind of an exponential curve. But this is not exponential. I mean, it is exponentially increasing and then it's having a plateau and then again increasing. It's very typical of the crosswind oscillations. This is another case. Again, it's more like a rectangle. In this particular case, the height is 170 meters. The height by width is 4.5 and scruton number is 6.5. And then you can see the response. You can have double hump. See, MOI has two humps. And one, when the wind is coming about 100 degrees, you are getting a vortex shedding hump. and another one at 280 degrees, again you have another hump. And exactly same thing happening in MX, but for opposite angles. So you have one at about 200 degrees or 190 degrees, and another one around 10 degrees. You have two humps. So you can easily notice that where this vortex shedding is happening, whether it is too high or not. So here you can easily recognize that, especially in MX, these peaks at 190 degrees too huge compared to your long wind, because your long wind is around 100 degrees. So you can see that number is around 1.8 versus this number is 3.5. So it's almost getting double actually. This response is double, crosswind response is double in comparison to long wind response. So this is a problem. And if you just follow the code and try to estimate the long wind, then later you realize that your loads are too high and now what to do. So that's why you need to be careful right from the beginning in terms of whether the shape is going to have any crosswind issue, how do we arrest that, and what are the techniques one can use it. Yeah, again, showing the spectra, you can see the spectra is very peaked, and try to plot the 700-year return period wind speed as well as 10-year return period wind speed. This is plotted in terms of reduced velocity. You can see the 700-year is right at the peak. So this is causing a lot of issue with the load, actually. Not too much with the acceleration, because the acceleration is down in the spectra. It is at the downward slope of the spectra. So your intensity of acceleration is not too much compared to your loading. Loading, it is getting affected too much. And you can again plot the mx versus wind speed. You can see this is something interesting. You can see the 170 degree response. 170 degree response is nice. There's no hump or anything. You can see it is just increasing and increasing when the wind speed is increasing, which is very typical. But when you look at 180 or 190, that is not the case. It is just taking off and then having a plateau after some time and then again increasing. So this one is very, very important. Okay, so this is where the vortex shedding is happening, which is causing the response to be higher. Now, a little bit more on the crosswind spectra, because we have studied quite a bit on crosswind spectra. So depending on the shape, the spectra itself will tell you all the story in terms of whether it is really going to be too much or not. So if you look at 6:1:1, the spectra is very peaked. That's a solid line. But as soon as you go into 6:2:1, that means the wind is coming across a broader direction. You still have a hump, but that hump is very low compared to the square cross section. So the rectangle cross section is giving kind of less of an impact for the crosswind in comparison to square cross section. Square is giving very high impact. So, but when your wind is coming across the narrow wind direction, then your response is more broadbanded because it is getting attached to the side. So it is not giving too much crosswind. You can also see the aspect ratio impact, because 3:1 to 4:1 to 5:1 to 6:1. The 6:1 is getting peaked and peaked and peaked. When you go from 3 to 6, you can see each time it is increasing and increasing. So when the slenderness is getting increased, you are going to have serious trouble in terms of crosswind oscillations. I'm not going to go through the rest. There are lots of comparisons between the code and the wind tunnel and etc., which I think if you're interested, I can send a paper on it. So here, another aspect of it, this is more on plan dimension. This is a rectangle. So you have 2:1 rectangle. So you can see A is all 2:1 rectangle. Then you go to B, you'll see 3:1 rectangle, and then 4:1 rectangle. So vividly, you can see the impact it is reducing and reducing, because here the wind is coming across the broader direction of the rectangle. So when this aspect ratio is getting increased, 1:4 and to 3:1 to 4:1 to 2:1, you can see the 2:1 has the peaked spectra in comparison to 4:1. So what this means is if your rectangle is getting elongated, then your crosswind chance is decreasing. Okay, because the most chance is for 2:1 rectangle in comparison to a 4:1 rectangle. Here, the impact of the height is not that vividly can be seen, which I don't want to discuss too much, and maybe we can take it up for discussion later. And you can go through that paper as well, because here more about the plan dimension aspect ratio has more importance in comparison to the vertical direction aspect ratio. Now, this is all good, but the trouble is we want to somehow eliminate or try to reduce the impact of this. So that's where I think our ideas should come. So first of all, the mitigation measures through geometric modification. If I am talking everything to a structural engineer, that is, I think the structural engineer may not have much of an impact on this particular issue. Here, mostly the architects have a lot of things to say. They have more, they can impart more impact on this particular aspect. Look at what happened in Type A 101. Type A 101 initially was a square structure, but when we estimated the load acceleration initially, we found out that it is going to be huge. And plus, Type A is a very high wind speed region. And we cannot build really 505 meters with a square shape, even with a damper. Because the loads are going to be huge and we had to reduce the loads as well as we had to reduce the acceleration. So we tried different shapes and you can see the various shapes. And then finally, the shape of double step corner has been accepted for construction. And the impact of that you can see immediately from this graph. This is the RMS value of crosswind shear force. And you can see 1/10⁸ is Newton is the RMS value for a square versus compared to almost 6/10⁷ for this shape. And there is no inertia or anything here. This is purely the impact of the shape. So the shape can really do the magic in terms of reducing the impact of this vortex shedding. So we learned quite a bit, not just from this building, from a lot of other applications of aerodynamics as well, and then utilized in many of our structures. Look at this particular case. This is another interesting case where the one on the case one is an octagonal shaped building around 320 meters tall. And the one on the right side, case two, is almost like a square structure, which is 180 meter tall. Then you look at the statistics of this. This is where it is important. CD bar, which is the mean drag coefficient, 1.3 versus 0.6 for an octagonal shape. The load is almost half now, the mean load. And when you look at the CD tilde, which is RMS 0.43 versus 0.1, it is like 1/4 of this. Then if you go to lift means crosswind oscillations. So this is RMS fluctuation 0.97 versus 0.06. It's almost not there. It got killed basically. There's no vortex shedding. It is gone. So it is all about the shape. So Shanghai Tower, this tower is basically designed in the wind tunnel. So we had the option of twisting this tower to various twists to reduce the load. So you can see 120-degree twist, 80-degree, and 110-degree twist, and etc. to see what kind of twist will give the reduced load. And plus, there is a hole also at the top. As you can see, the World Trade Center just beside that is also one of our project done long back where there is a hole as well at the top. This could have huge impact on the base moment actually, because as you know, the top 1/3 is giving a lot of base moments on any structure that you take. So this particular Shanghai tower is, I think the final configuration is around 120-degree twist, which had the least load on that tower. This is picked up from Tanaka et al. Paper. So this again showing the hump of the spectra, and the spectra is getting hammered down. when you have different shapes. Actually, you can see the steps and twisting always nice when gets confused, basically, because there's no clear shape actually as you go up on the structure, so it is getting hammered down, and this will have the least response likely. So look at some of these towers, 364-meter tall tower, 500 meters, 275 meters, and none of these towers have any crosswind issues, just because of its shape. So you can see the shape; it's kind of rounded, have hole at the top. Here the corners are chamfered. Here it is rounded. There are many new structures coming with similar ideas. So you can have steps, you can setbacks, etc., and etc. Basically, you don't want to give a constant shape to the structure. You want to confuse the structure, confuse the wind, not the structure. I mean, you're confusing the structure as well. But here again, I mean, you can see the corners again, chamfered and I mean, step. Uh, and you have some openings as well. So there are many techniques one can use. But again, I mean, this is something we have to basically uh, tell our colleagues, of architectural colleagues, to look into it very carefully whenever they are coming up with slender structures. So I came up with some kind of a table where what can we do? Corner modifications. You can do all these kind of shapes, which is good to reduce crosswind. Um, every shape has its own uh, story to say, but typically all of these shapes will work depending on, I mean, in some cases they go and have a small rounded corner, so it depends on how far you can round the corner. So I have written here corner modification of the order of 10 to 20% of the width are required to achieve noticeable impact. You can also have corner slots, so you can have gaps, you can have fins to confuse and disrupt the vortex shedding which is happening at the corners. So there are various techniques. Again, you can have a screen. Typically, shrouds are used in chimneys to reduce the vortex shedding. So those kind of techniques can be utilized even in tall buildings. There's a possibility. And you can have corner disturbances, sometimes protruded out balconies would be good. So you can see various cases where fins and balconies, especially at the corner, if you have fins in the middle of the structure, there's no use because vortices are being shed at the corners. So you want to do something at the corners, about 10 to 20% of the width. You can also have tapering, you can have twisting, you can have roundness, you can see all of these shapes. I mean, we have been seeing such twisting and tapering nowadays on a lot of structures. There is another technique which is also being used nowadays, the rooftop features, because you can see some of these structures have confusing rooftop. Nowadays we have crowns, we have all kinds of stuff which is at the top of the roof, which will have its own impact in terms of reducing the crosswind. So geometric modification is extremely important. Now you can see the crosswind spectra again for this particular structure. For 6:1:1 open case, it's a square structure. You can have such a huge hump in the spectra, but the red dots are showing 11:1:1. It's a very slender structure. It has a reduced spectra, reduced hump. You reduce the impact of it through this corner modifications, through these openings at the rooftop parapet, through these openings at the mechanical floors. There are a lot of things done on this structure to go from that point to this point, to reduce the impact of it. So one can really do the magic. And there are other cases. So in this case, you can see one is a rounded edge with some protruded out slabs and things like that, which will again kind of helpful. Then this particular structure, which I showed before, has a hole at the top with round. You can see these spectra. One is the dotted blue line, which is very low hump. And then you have another one, 9:1:1, which is a green line, which is also very low hump, actually. So basically, through this process, you're basically killing the vortex shedding on the sides of the structure. Now we come to structural modification. Structural engineers also can do some modifications on their structure, but the trouble here is the spectra is peaked. So you have an issue with the load. You may think that, okay, let me stiffen the structure or let me flex the structure a bit to avoid this issue. So when you do that, you may have another problem from acceleration because acceleration may go higher or lower. So it's not easy to fix it, but you need to think about it, how to fix it, because when you try to fix one thing and you may create another problem actually. So it is not an easy fix through structurally, especially when you have crosswind issues. So that is why geometry is the first line of attack. Actually, that's the easy attack where one can really do the magic. But here too, you can play with this, do the sensitivity. Increasing mass is not an option in reducing, crosswind load, but you can reduce the crosswind acceleration because increasing mass will be always helpful in reducing acceleration, but not on load. Load will stay exactly at the same point. And you can also do sometimes advanced wind tunnel tests. You can have a elastic test to understand any positive aerodynamic damping is coming into picture. You can take advantage of that. And you can reduce the response to the structure through a positive aerodynamic damping. So this is Kingdom Tower in the tunnel, and this is an aeroelastic model. I'm not going to explain this for the interest of the time. You can see the Burj Khalifa went through several aeroelastic studies as well. Again, I mean, we benefited out of those studies. We reduced the load, we reduced the acceleration by doing aeroelastic studies. And we have done this, I have shown before. So we have done a number of different types of tests. One is to 500 scale test, one is to 200 scale test only for the steel portion of the Burj. So that also been studied separately. We also studied the Burj in the large scale test as well, a bigger model to understand the Reynolds number sensitivity. The last item in my presentation is supplementary damping. So you played with the geometry, you played with the structural properties, everything is helpful, but you're not there yet. So the last option, or sometimes it could be even the first option, but you look at the damping because sometimes you can lighten the structure and then you can put a damper to arrest the motion. So that's another way, I think, especially in cities like New York, where there is no lack of space. You don't want to, reduce the interior space. So you want to keep the same space and go taller. And the building could be lighter also over that part of the world. So it can move. So put a damper at the top. There are a number of buildings there having damper. So roughly speaking, the damper goes either tune mass damper or tune liquid column damper. I'm not going to be talking about other types of damper. This is superior density. Cost is a bit high, but you can get higher damping. But here, low density, the cost is low, but you cannot get too much damping out of it. But still, you can fairly get 2, 3, up to probably 4% extra. Type A 101, everybody knows. I think I'll quickly go through this. You can see the damping one solution. So this is the damper motion during typhoons. So we have been monitoring this damper for a long time, so we know exactly how it is performing for the last 25 to 28 years or so. This is 111 57th Street, also has a damper at the top. This is 435-meter tall building with 24 aspect ratio, very slender building, which has an 800-ton damper at the top. It's an inverted damper. So you have two types of mass, one hanging in cable, one is on a pedestal. So it's a patented system. So it can give around 6% damping, extra around 5% damping extra, in addition to the 1% damping that we have taken for structural. This is the damping we used for Shanghai Tower at the top. TMD floor, 125th floor, 578 meters. This is about 1,000 tons. This is a tune mass damper as well, which gave around, I think, close to 3 to 4% damping extra. You can see the final response. So it was without a damper, it was here, but with a damper, it came down. So it's mostly about mostly in these cases about acceleration. Sometimes it's about drift too, but not for reducing loads. Tune sloshing damper. So instead of having a tune mass damper, you have water tanks. Nowadays, I think everybody is having water tanks at the top. So they want to tune that water tank. You had to have a special design. It's not like just a water tank. So you had to do a proper design. You can have screens and etc. And you can get some damping out of this oscillation of the water through these screens and post and etc. So you can see the fluid motion is down due to the turbulence caused by flow restrictions like screen and post and lures can be utilized inside this water tank to get some damping out of it. So we do mock-up test as well inside the tunnel to know, I think once the damper is being designed, we do mock-up test in our lab to confirm that this is all going to work exactly the way that we thought it is supposed to be working. So this is the Random House New York damper. So it's a tuned liquid column damper. I'm very close to finishing my presentation. That's about it. So concluding remarks. Assessing crosswind response of slender building is very crucial for design because if you don't assess this in advance, and it's a problem because if you think that it's all about a long wind, that may not be the case. Then you will be taken taken for a ride later. Actually, so you need to be very careful. Early stage evaluation by experts are essential. Evaluation using standards, exercise some caution because it's not going to tell you the complete truth. It can give you some numbers, but you have to also have something in your mind whether the shape is going to be giving me this much number or even higher number for that matter. And also, as you know, 6 is to 1 is to 1 or 6 is to 2 is to 1 is the maximum that I think the codes are covering. CFD is a good tool for preliminary evaluation. If you have good tool, I mean, this can give you some idea about how your shape is going to be impacting, how your surrounding is going to be impacting. Geometry and its surroundings will influence significantly because that's one of the issue because we don't have any more squares and rectangles. We have structures with all kinds of shapes, with crowns, with openings, with fins, with you name it. So, and you have all kinds of surroundings as well. So that is a serious issue to look at it. Wind tunnel testing is the only solution, I would say. I don't think any other solution which can really say concretely about across impact at this point. No other tool is, to concretely say, no other tool is there yet, actually, I would say. Finally, mitigation provisions can be tested to confirm because once you have a solution, you can easily test it in the tunnel and confirm it that this is the solution that is going to be working, not only just from structural point of view, but also financially. That's about it. With that, I conclude, and I hope I finish on time. Now we have some time for question and discussions. Thank you.
Right. Thank you, Dr. Suresh. Right on time indeed. Thank you very much. Very insightful presentation, particularly the animations that you've used, which help to visualize the movements and the behaviors. You also touch on the mitigation measures with very interesting practical examples. And whilst you were saying that this is more obviously of an architectural decision, I truly believe that we structural engineers are also at the heart of the decision when it becomes a discussion around more material, more loading, more carbon, more cost, and so on. So it's a team's effort. Yeah. Thank you. Thank you
No
very
problem.
much. That was really, really interesting. I'm going to open the floor now to questions. And I will start with the first question from the YouTube,
Yes.
from a structural engineer.
Yep.
Hi, Dr. Suresh. Thanks for this informative presentation. I saw a lot of engineers using the CFD to design their building on wind load with ignoring the building code. What is your thoughts about this?
Ignoring the building code. Well, I think the building codes have limited options in terms of crosswind loads. It has some information. We can utilize that at the beginning to understand. But I think CFD is one step ahead of the building code, I would say, if it is properly done. But that cannot be the final answer, though, especially when your building is very slender. So you have to go back to the tunnel to find out the exact answer, not through CFD at this point.
Right.
Yep.
Thank you. The questions start to come up in the chat box.
Yeah.
Question from Three Leaves. What are the latest advancements in wind tunnel testing for tall buildings?
The latest advancements, basically at this stage, uh, we start with the rigid model test and followed by aeroelastic. So in aeroelastic itself, there are a number of different aeroelastic one can do. You can start with the, uh, simple aeroelastic followed by spine system aeroelastic. The aeroelastic can be very complicated depending on what you wanted to include in aeroelastic. Sometimes you have to deal with only sways. Sometimes you have to deal with the torsion. If you want to deal with torsion, then it's going to be quite complicated aeroelastic. Other than that, I think you can also do time domain simulations nowadays. I think one can also do time domain simulations. You can measure the time series out of your force balance or HFPI and utilize that and do the rest of the things in the computer, especially because nowadays I think the performance based design and etc. people are using a lot of time domain simulations as well. But from internal standpoint, I think mostly elastic is the ultimate at this point.
Right. Thank you. Question from Sama. Interesting session. Today's session is more about a crosswind, but I have a question about large open structures, canopy type uplift.
Oh, canopy type uplift. Typically, there is no crosswind in that case. Because if you're talking about, I think if the question is concerning a roof structure, we generally don't see much of a crosswind or anything. It is mostly about uplift. Of course, uplift edges, you might get some vortex shedding. But when you're talking about large span roof, then I think the overall roof uplift and downforce, that is not really a crosswind issue. Um, it is, of course, there is some suction happening at the rooftop. That doesn't mean that it is going to be similar to a tall building case. You can get high uplift, but when you're talking about structural load, typically it is getting kind of averaged out. So you don't get like super huge uplift on any roof you take if it is a long span roof.
So in terms of method of assessment, Dr. Suresh, would we stick to codified values or do we any
Interesting.
insights on? Yeah.
Okay, from the point of view of assessing that, you can use codes, but the codes are built for not for large span roofs. Generally, all the codal values that you see for roofs, mostly for smaller roofs, not like long span roofs. So because of that, what I can say is that if you do internal or even CFD for that matter, your loads are supposed to be lower compared to a code value. As codes are predicting very high values on roof. And if your roof is a long span roof, then definitely your values are going to be low. It could be sometimes very low compared to what you see on a code.
Thank you, Dr. Suresh. Thank you, Sama, for the question. Another question from Shazeb Mirza. Question from a beginner in the field of design and analysis. If we have already designed a structure for lateral seismic forces using the equivalent lateral force method or response spectrum analysis, resulting in significant base shear and making the building considerably stiff, why is it still necessary to design it further for lateral wind forces?
Can you repeat that, please?
So if a building is already designed compliant with the code to resist seismic forces using any
Oh,
method,
uh-huh.
why, and it's already stiff and it has significant base shear, seismic base shear, why is it still necessary to design it further for lateral wind forces? Is
But
the question.
yeah, but we design either for earthquake or wind, whichever is the biggest, right? We don't typically the designs are not happening combining both of these loads. So maybe if one of the structure is uh, dominant load is wind, then you design it for wind, but certain elements could be designed for detailing could be where the seismic load may get involved. But if it is a lower structure, there's not a lot of height. I think below 30 floors or even 20 floors, likely the seismic will govern. So then there is no question of wind actually.
Yeah,
So it depends on which one is governing. So if it is slender towers and taller, then definitely wind is going to govern. Even in high seismic zone, there's a likelihood the wind will govern.
right.
Yeah.
Thank you. Another question from 3L. How do dynamic responses to wind loading differ between rigid and flexible tall structures?
Okay, rigid. See that that definition is a bit vague because many codes will say anything more than 1 hertz it is rigid. A number of codes have this definition. Less than 1 hertz means it is flexible, but that's not completely true because especially in tall buildings, if your frequency is going beyond zero point 0.5 hertz and etc., then in the influence of inertia is not huge or not sizable contribution from inertia. But if it is below zero point 0.5 hertz, likely you're getting more and more inertial contribution. And then if you're coming to zero point 0.3 and less and zero point 0.2 and less, then it's getting really, really significant. So it depends. Uh, I mean, the code has its own calculation in terms of rigid structures. I think, especially AC, they're using 0.85 or something. So there's a gust factor. And if you have flexibility, then of course your that G will increase and you can go to beyond 1 and etc. Australian code does the same. So, but in wind tunnel, we can easily come to know about these things because we can get mean load, background load, resonant load separately. So you know the contributions of each one of the items. Typically, tall buildings are all below, most of the times below zero point 0.4 hertz, zero point 0.5 hertz. So where you can notice the inertial contribution.
Thank you. Question from anonymous attendee. In your experience, will the buildings constructed around the buildings that we already designed at a later date will have any impact? Should we recalculate the wind load after the new buildings are constructed?
Okay, so this question, see, typically when we do the test, we do the test of existing conditions. We also look at the future conditions. We think about that. If there is something known, then we'll put it and do the test as a second type of test, second phase. But if you don't know, then you can't put it. Later on, some building comes up, there is a likelihood for skewed angles of attack, you can have some higher loading. There's a potential, but that is only for skewed angles of attack. But then nothing we can do at that point. Over the period of time, the city will grow, and then the space will get filled up with other types of buildings and etc. So your this particular effect will vanish over a period of time. But this is something we believe that whatever the cushion that we have in our design will take care of this, especially when the capacity of the building I don't think we ever understood fully the capacity of each building in terms of its strength. Because until we do the performance-based design fully, there is a lot of cushion, I believe, in terms of the capacity of the building.
Sure. Another question from the anonymous attendee. Can you throw some light on the cost? I'm sorry.
No problem.
The cost effectiveness of the super tall structures with a now trigger system or dampers.
Okay, so in terms of cost, it is difficult for me to address. But you have to look at each case because I say the damper cost, I think most of the time it'll come to know. I mean, TMDs are depends on the size of the TMD and etc. So you can easily know the cost in advance, and you can also see the cost of outrigger system. But how far this outrigger system is going to help is another issue, because like I told you before, I mean, outrigger system, you're trying to stiffen the structure and etc. You may be out of one trouble and getting into another trouble. So you need to evaluate, because the damper, regardless of what you do, it will be always helpful because it can reduce the drift, it can reduce the acceleration, it can even reduce the load actually, even though we are not taking that into account fully. But if you have redundant system, you can always even reduce the load actually. So, but the stiffness increase can have some impact, but how far it will impact, you have to look at it. It may be helpful in reducing one of the issue, then creating another issue. So that needs to be looked at it, and then you can make a decision, especially with regard to that particular impact as well as the cost.
Thank you. Very interesting question from Sama.
Yes.
Understand many sensors are placed at Burj Khalifa to assess deflections. Any comparison of wind tunnel to actual condition of sway?
Good question. I think we know some motions which happen in certain storms in Burj, and it is still within the limit. And more than Burj, we know such motions happen in Taipei 101 because that has been observed for the last, I would say, 25 years or so. And we have predicted with the damper, without damper, what is going to be happening to that tower 25 years back in the wind tunnel. And that prediction is still holding true even after a lot of typhoons pass by. So we know the motions of that damper more than, I think, especially with the damper, I think we have good observation on that particular tower. With the birds too, I think there were some decent enough motions a few years back. And those are again, I mean, that is again at the tip. Actually, you can imagine the top is steel and is getting reduced. So there could be oscillations at the top, not at the place where people are staying, which is well within the limit. And as you know, there's no damper on that tower as well. We had a provision, but we didn't put a damper on that tower, which is not required.
Hope this answers the question, Sama. Thank you. I'll take two questions from the YouTube.
Yep.
One from Rahul Leslie. In
Yep.
slide 19, not sure if we can go back there. The graph shown, is it wind spectra or spectra modified by aerodynamic admittance? Slide 19.
Oh, this is the one. Yes.
So is this wind spectra or spectra modified by aerodynamic admittance?
Just a minute. Oh, there's some problem here. Yeah, this one is aerodynamic admittance. Yeah, this is after aerodynamic admittance only
Okay.
because yeah, this see, we are not separating aerodynamic admittance in this case because we are measuring the force, and then we are taking a spectra out of that. That means it is not just the oncoming flow; it is hitting the structure and changing the body induced turbulence. The body has its own inducing some turbulence as well. So aerodynamic admittance is already included.
Okay, thank you.
Yeah.
And another question from YouTube. Would a ratio of 5:1 be considered as a threshold for requiring further investigation into a crosswind effects? Is there a
5-1,
threshold?
5-1-1 may not get into any crossing.
Mm.
Yeah. That is 5-1-1. Oh, you mean to say 5-1-1?
Slenderness.
5 is the height, right?
Yes.
Oh,
So,
no, I wouldn't do that. I would say 4-1-1.
okay. So anything above 4:1
Above
would be
4-1-1, yes.
yeah. Yeah.
Mind you that I think all of you are using code. If you are looking at Australian code, they even start from 3-1-1. Okay, so their spectra starts from 3-1-1. So I would say roughly 4-1-1.
Okay.
Yep.
Okay. Thank you. I don't see any more question. I will take the liberty to ask you a question, Dr. Suresh.
No problem.
I was very interested in positive aerodynamic damping that you have touched on in the presentation. And you had mentioned about the advanced wind tunnel testing to see if there is any positive aerodynamic damping. What sort of range of percentage damping we may get from that, like in your experience? Is it like a substantial, because there's a cost impact, obviously, if we go for the advanced modeling.
Right. See,
Or,
you have
or is
to
there, yeah.
you had to initially do some computation and see the expectation, because if the structure is very slender and sputter number is very low, there's a chance of a lot of motions. Then you are doing the elastic test to see any issue with the negative aerodynamic damping rather than positive aerodynamic damping, right? Because otherwise you are predicting the response from rigid model test. So if you do a elastic test, maybe if there is a potential for negative aerodynamic damping, your response can be higher compared to a rigid model test. So that is something to be watchful. So what one has to do is look at the scruton number first and see where you land in scruton number, look at the shape, and then decide what is the best option. Because if you're expecting some super tall buildings with a little bit higher scruton number, but it is very slender, then there is a chance of aerodynamic damping. For instance, you can get, I would say, based on my experience, you can get anywhere from 0.5% to 1% is a possibility.
Oh,
Okay.
okay. Yeah.
So
Yeah.
it's not small actually.
Yeah.
So it can be sizable contribution actually, and which can reduce the load actually.
Of course. Of
So
course.
yeah.
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 Yeah. Very good to know. Thank you.
Yep.
I think we will stop here.
Okay.
Many questions came in. Thank you.
Yep.
Yes. Did I miss
Yeah, we have
anything, Hammond?
quiz. Yeah, we have prepared a quiz based on the presentation, and we would request all the participants to answer the quiz. So the quiz will launch now.
Okay.
So it will help us to see the focus of our attendees. The first question: 3 buildings, all 300-meter high, rectangular in plan, 20 meter by 80 meter, 20 meter by 40 meter in plan, 20 meter by 60 meter, which will have highest across wind moment.
Thank you, Hammond. Great questions.
So let me share the response also with our yeah, all our attendees, they did good with square plan S equals to 0.1, it will be And Taipei 101, it was corner setback and maybe this will be 20 meter by 40 meter. It will be having highest across wind.
Yeah, I think there one of the comment that I have with that one is, of course, there is the platform ratio is getting more closer to square, so that will have the aerodynamically that will have the impact for sure, but that doesn't mean that necessarily the crosswind moment is going to be higher because your width is low. You understand? So the potential is very high, but the actual answer, so it has to be more like not the highest across wind moment. It should be more like the question of highest across wind moment coefficient. Because otherwise the trouble is when the width is low, obviously your load is supposed to be lower as well. But the potential for the impact is high. Okay, so the coefficient will be high for sure, but not necessarily.
Yes. So now second also answered very well. Third also answered very well. So it shows all our attendees, they were focused. But here, tune mass damper will achieve reduce acceleration, floor motion at the rooftop. Thank you.
Thank you, Hammond. That was a really nice addition. I wonder whether we have the best perform or the top scorer. Maybe we can work on this next time. Dr. Suresh, I wish to thank you wholeheartedly for a very, very interesting
No problem.
presentation indeed.
Yes.
Thank you. You
No
are
issue.
based in Dubai, so I'm sure a lot of us will come across you and
Yeah,
ask you maybe more questions in the future.
definitely.
Thank you.
Anytime, please contact. Yeah.
Sure.
Thank you.
Thank you
Thanks a
for
lot.
your time. Thank you,
Thanks
Hammond,
everybody.
and thank you all
Thanks.
for joining.
Thanks. Thank you. Thanks
See you
everybody.
soon.
Yeah. Bye-bye.
Bye.
Bye-bye.
Yeah, we can leave now, Dr. Suresh.